Hello. In this lab, we will talk about sequences and series. At the end of it, we will also talk about limitation of Python when dealing with convergence of series. We will also introduce a new library, mpmath, for which I will use the shortcut mm. Throughout this file, for SymPy, I will use a variable n. For the most part, it will be positive integer, but not always, so I will not specify it here. So now let's introduce our sequence. I'll have a sequence a sub n equals 1 over 2n plus 1. So this is 1 over odd numbers. To create a sequence, it's quite simple. I will use sympy command sequence. So here I have an equals sp.sequence. Then we write nth term, so 1 over 2n plus 1. And then we write the range for your n. So I want my n to go from 1 to infinity. So let's see what my sequence is. So that's 1/3, 1/5, 1/7, and so on. Next, let's plot it. So we want to plot first 30 terms. So I'll create my list here from 1 to up to 31 with a step of 1. Remember, the last upper bound is not actually being used. So since my step is 1, I will have only integers, and the last integer before 31 will be 30. Then I will use a command scatter to plot my points. The reason why I'm using scatter here and not plot is because if I try to plot multiple points using plot command, it will try to connect them with line segments to create a graph. I don't want that. I want all of my points to be just separate points. And for that, scatter is a better command. Inside scatter, we have our 30 numbers. So n goes from 1 to 30. And then, in essence, the y values, which will be the values of my sequence, 1/3, 1/5, and so on. And I want to take only the first 30 terms. Remember, the amount of terms in nval has to match the amount of terms here. So I have to limit my list. I cannot take all of it. I need to only take exactly 30 terms from it. So the syntax here is the same as the syntax for any list and array. I have a column here. Any number before it means where I start. Since I have nothing, by default, it will start from the beginning of this list. And the number after is the upper bound, again, not including that bound. So I will go up to 29th term. Why 29th term and not 30th term? Well, because the indexing of lists starts with a 0. So my actual 0th term here is my first term of the sequence. My first term here is my second term in the sequence and so on. So there's a shift in the indexing. You have to be very, very careful about that. And that's it. The rest is just to make my graph pretty, giving it a title, labels, and a grid. And so here is. These are my first 30 terms of my sequence. And as you can see, the sequence is a decreasing sequence, and it most likely approaches to 0 here. So now let's find and confirm this limit. We will use command sympy.limit_seq. So it will find limit of the sequence. What we need to give it, we need to give it the nth term of the sequence. And to do that, we'll write an.formula. So the difference between an and an.formula is that an is just a list of numbers, while an.formula is the nth term. So it's an expression for the nth term. And of course, we will give it the variable that we're using, n. If we run the command, we get 0. So the limit is indeed 0. Now, since an.formula is just an expression for n term, it's basically a function of n. And so we could have technically used here just a regular limit command. So we will give it an.formula. We'll specify this as a variable n, and n will go to infinity. And we indeed get 0 as well. So why would we choose to use limit_seq instead of a regular limit? Well, limit seq assumes that n is an integer. So it will never consider any other values for n. While the limit command will think that n is a real number. So it takes all the values going to infinity. This will cause the limit command to fail sometimes, and specifically give you the wrong answer. And one of the problems in your problem set will be to explore exactly when this happens. So next, let's look at series and partial sums. We will consider a series of -1 to the power n over n as n goes from 1 to infinity. So this is an alternating harmonic series. And our first goal is to create a list of 30 partial sums of this series and then plot them. So first, let's create the list. So we have here an expression for our nth term of the series. So it's -1 to the power n over n. And now we are creating a list. So these brackets on outside signify that this is a list, and anything I write inside is part of that list. Now, the expression inside is a little bit more complicated, but in essence what that is the hidden for loop. So here I have a for loop, so for k in a range from 1 to 31 with a step of 1. So k will go from number 1 to number 30. And for each of those k, we will calculate a sum. So it's a sum of these n terms as n goes from 1 to whatever my k is. So at first k is 1, I'm going to have just the first term. Then k will be 2, so it's the sum of the first two terms. Then k is 3, it will be the sum of the first three terms, and so on. So if I run this, that's pretty much just shows you what that list is. So it's first term is the sum of -1 to the power n over n as n goes from 1 to 1. Then it's from as n goes from 1 to 2, from 1 to 3, and so on. If I really want to see the numbers here, I can, for example, use n function, or I can maybe use evolve. And now you can actually see the numbers as well, so it evaluates them. We can also look at each term specifically. So here, let's say I want to look at the fifth partial sum, which again, that's actually a sixth partial sum. It's a sum of the first six terms because counting of lists starts with a 0. So there you go. This is a sum from as n goes from 1 to 6 of -1 to the n over n. Of course, if I use n on that, it will actually evaluate it. So I get negative 0.61 and then 6 repeating. Next, let's plot it. So it's very similar to how we plot sequences. In fact, it's pretty much the same. I have my n values. Again, it will go from 1 to 31. I want the first 30 terms. I will use scatter plot again. And here, this is my list of partial sums. Notice I don't really need to specify my upper bound here. This is not an infinite series. In fact, number of terms of the whole list of partial sums is equal to the list of n values. So it's exactly the same. There are 30 values in each. Let's plot it. And there we have. So as you can see, it jumps around and it seems to converge to something around negative 0.69, somewhere there. So now let's see if it actually converges to something. So if I would keep adding this series as n keeps going up and up and up and up, right? Will it actually converge to something? So in class, we usually consider a limit of partial sums, for example, but here we cannot really do this. So instead, we will just try to add it. So I will use a command from SymPy summation. So I give it an nth term, and then I'll say that n goes from 1 to infinity, so it's a full sum. And I will use n function on it to evaluate it. And we get some number here, negative 0.693, and so on. We can also use the new library that we introduced, MP-math, to do the same thing. So here I have mm.nsum. So it will do the similar thing. It will add things up. Then I create a function, lambda n. And so this function is -1 to the power n over n. And my and will go from 1 to infinity. So here infinity will be represented as mm.inf. And by the way, if I have any other functions inside, like a sine and cosine, I would have to use this new library here. So if I needed a sine, it will be mm.sine and so on. So let's evaluate it. And as you can see, we got the same answer. Notice this was actually a little bit quicker to calculate. Usually the MP math is much quicker in calculating something. However, it's also less precise, and you will see this later on. So next, let's talk about limitation of Python when dealing with summations, specifically convergence of series. So in this example, when we calculated both summations, we got the same answer, and this answer in essence fits with what we see on the graph here, which strongly suggests that this is in fact the correct answer. But we have to be usually quite careful in determining that. So here's one example. Let's say I have an harmonic series. So here I have a sum from 1 to infinity of 1 over n. As before, I will create my nth term and then I will use summation. No problem here, we got infinity. But this is because SymPy didn't actually try to add this up. It knows this is a harmonic series, and so it knows the answer is infinity. If I would use nsum here, it doesn't know that. It's not a symbolic library. It will just try to calculate the sum. And as you can see, I get some answer, 9.4. So be careful, because this is not a correct answer. Because this is a divergent series. It doesn't adapt to anything. Now, how do I tell that this is a divergent series? Well, I can see that, first of all, summation, SymPy, gave me infinity. This by itself already means that this is a divergent series. But if I check and sum, I also see the answer here doesn't fit with the answer here, which generally also means it's a divergent series. Let's look at another example. Let's say I have a series of sine of n as n goes from 1 to infinity. If I use a summation, it will take a little bit of time to calculate. And here's the answer. It's a very large answer. As you can see, it's 10 to the power 129, but it's not infinity, right? So it's a very large number. So is this the correct answer, or is the series divergent? Well, let's calculate nsum, and which, by the way, notice it will be much faster, almost immediate. Well, I got here 0.91, which is quite different of the answer from we had before. So which one is the correct answer? Well, neither of them. This is actually a divergent series. And one way we can see that is that the answers are different. So if the series was convergent, we would have gotten the same answer. So this is a little bit tricky, and you have to be very careful in understanding your answers. This is also why you kind of need to know a theory of convergence of series to really make a correct call. The Lab5 will have three problems. The first problem will deal with the difference between limit command and limit of a sequence command. The second problem will deal with convergence of sequences. Finally, the third problem will be about series and understanding the convergence or divergence of series. So here you would have to compare summation command and the summation command from the MP math, and also graphs of partial sums.